Yes, hello everyone. My name is John Trevor Kasule, and I'm going to be presenting with Iga Gilbert, and our topic is quantum-assisted deep learning approach, dementia screening using speech-based biomarkers and spectrum analysis. Yes, just to introduce about the topic, dementia is a global disease and affects about 5 million people globally, and this is the predicted to rise to about 139 million by 2050. Yes, amongst the common degenerative diseases amongst the elderly, and it's important to detect this early because it helps people to intervene and maybe help the patients very fast. But this mostly relies on expensive and intensive tests like the MRI and other assessments for the cognitive health. Speech impairments are very key in detecting dementia. Patients who have dementia can easily have speech impairments, and these can be big biomarkers for analysis. AI-driven analysis can provide a cost-effective and scalable dementia screening by targeting these speech impairments. This study integrates two things: deep learning, speech extraction, and also quantum protector machines for classification dementia patients. Yeah, problem statement. We realize that one of the challenges faced by people in dementia diagnosis is expensive and time-consuming traditional methods like the CNNs and the RNNs and all that. However, there is also limited the availability of neurologists in many regions across the world, and this is common across everywhere in Africa. And there's a big bias in existing AI models, the CNNs and the RNNs, that are mostly trained on standard data sets. Then it's also difficult in detecting early-stage dementia using conventional screening. We realize there's a need for an invasive and AI-powered speech-based dementia detection tool, and this brings us to our solution. So our solution integrates two things: a hybrid AI model that combines classical deep learning and quantum learning. Yeah, we propose to have the following. Feature extraction, we want to convert speech signals into spectrograms, and then we want to use spectrogram to extract the features from the spectrograms, SqueezeNet to extract features from the spectrograms, and then use quantum assisted classification by applying the quantum support vector machine to be using quantum kernel methods. And our outcome, we expect to have a higher accuracy with optimized description resources. We also have efficient classification in source-constrained environment. Our methodology, we have the following. We shall have to compile the speech spectrograms using the short-time Fourier transform, and then employ the SqueezeNet to instruct high-level spectral features from the spectrograms, and then classify dementia and non-dementia speech using quantum supercomputer machines, and then evaluate performance using metrics like accuracy, precision recall, and the AUC ROC metrics. This diagram clearly shows both methodology and pipeline. We have the audios, then spectrograms, which are passed to the SqueezeNet for feature extraction, and then to the QSVM, and then shall be able to get a class from the last layer. We invite Gilbert to take us through our dataset.
Yes, hello everyone. Yeah, our dataset overview. The dataset is called Dementia Net, and it contains speech recordings for both dementia and non-dementia. So there are two classifications, and then we have speaker demographics such as age, gender, and ethnicity. Yeah. Then we have some agonistic features such as speak duration, pause frequencies, pitch, silence ratios, and others that at least give a validity of our work and details of possible extraction. And then the data is split into training and then the validation set by the provider. And it also has a separate metadata for both the dementia and non-dementia group. Next slide. Yeah, the data set, as you know, it's a speech data set with recordings, and then the features that can be extracted. We have speech durations, we have pauses in frequency, we have articulation errors, and then we have bit validity and spectral energy. All these are features that can be extracted from speech, giving validity of our methodology. And then the metadata insights include most of the we noticed that most of the subjects are 65 years and above, very old, with dementia rising from 75 years. Although when you look at our speech, you see that we have speech of them in different age ranges, whereby before they had the disease and after they had the disease, because the collectors of the data set were able to collect, most of the data set is collected from the public figures that were confirmed to have the disease after some period. So they extracted YouTube videos of them speaking before the disease and after the symptoms. So that is a range of audio files that we have that can validate our work. It has a gender balanced data set, and then there is also validity observed in the frequency, so in the fluency and the different time responses. Next slide. Yeah, so this graph tries to show the class distribution between the two classes that we have, that is the dementia and no dementia, and you see that there is really very little class imbalance. And since we have a fairly balanced classes, we shall need some argumentation because of the different reasons that you're going to see, you're going to evident with the different distributions that we have. You can go to the next slide. Yeah, when you look at the gender and the thetica distribution of both for the non-dementia individuals, you see that at least there is an imbalance based on the different the gender. For example, we have very many males compared to the females represented by the pie chart, and there are very many whites compared to the Black Americans. So there we shall need argumentation based on these features so that we at least try to balance the different aesthetics to have a balanced distribution. And this can be done. You can go to the next slide. Yeah, when you look at the age at first symptom distribution, this is the age at which a person who has the disease, the first symptoms were identified. So you see that most of them symptoms show up at the age of 70. Few of them at the little ages or very old ages. So there are higher chances of someone getting the disease at the middle age between the 50s and 90s. You can go to the next slide. Yeah, I was talking about data argumentation before. So these are possible argumentations that can be done on our data set, provided based on aesthetics. So the argumentation will be applied, not based on the class distribution, but based on the aesthetics and the age. But we shall take care of the class distribution so that we don't imbalance the class distribution, trying to balance the different aesthetics and age gaps. So we shall take care of at least maintaining a balance, the class distribution, but trying to raise the different aesthetic distributions in the graph. You can go to the next slide. Yeah, this is a dynamic range and a spectrocentroid analysis of the two different classes that we have. But when you look at the dynamic range graph, you see that the dementia speech has a low dynamic range, which could be a weaker vocal. This is due to the weaker vocal intensity in that speech. And when you look at the other right graph, it shows a less variation, indicating that there is a reduced pitch in modularization of the specifically the dementia speech, which is different from the non-dementia speech. So that shows that there are possible identified feature differences in the two different speeches. That is the purpose of this graph. You can go to the next graph. Yes, when we look at this OnNet, it shows that the dementia progress varies widely, with some cases lasting at around 20 years plus, or between 20 years. So they show that the progress lasts for around 20 years. So someone can spend their 20 years within the progress. Should I call it progress growth? So you see that at the early onset, dementia at around, let me say, between 55 to 65 years, often it has a longer disease duration than compared to the later offset cases. So possibilities that in case someone shows the symptoms at a younger age, they will have a longer, should I call it a lasting progress rate versus those people that whose disease are identified at a later age. So at least this graph was trying to show the duration of the disease against the age set. And those are the possible insights. So the takeaway from that graph is that early detection of the model would prioritize younger cases and is having a what? As having different progressions. Then when you look at this distribution, you see that for the dementia patients, they tend to have a longer speech duration due to the increased pauses and repetitions. So their graph, when you look at is it the right-hand side? No, it's the left-hand side where we have the dementia. You see that they tend to have a longer speech duration, and this is caused due to the increased pauses and repetitions compared to the non-dementia. So the speech length and gaps increase, and that indicates that these are biomarkers for our AI model. Yeah, you can go to the next graph. Yeah, this is a speech waveform analysis for a dementia person. So you can go to the next graph. And this is one for a non-dementia. So I think you can toggle them as I explained. So we can see the difference between the dementia speech graph and the non-dementia, because the dementia speech graph shows irregularity in the amplitude and the frequency pauses and reduced energy by the person who has dementia, who has those symptoms, compared to a continuous or few gaps by a person who doesn't have dementia. So the takeaway from this could be that the time domain feature could be an extracted feature that can help to consider that can be considered for our classification. You can go to the next graph, to the next page, sorry, the next, yeah. So we've not also balanced these two graphs. We are not able to put them on one single page for comparison. So I think you will toggle them, you will toggle the two graphs as I try to explain. This is the dementia spectrum graph. You can go to the other, and this is the non-dementia spectrum graph. So I think you can talk with them as I explained. So you see that the dementia speech has reduced high frequency components, and the energy is a bit weaker in the middle of different frequency ranges compared to the what? To the non-dementia. So the spectrogram confirms to be a distinct speech impairment for dementia. That means that our project is on the right track and we shall be able to extract the required features. You can go to the next graph. Yes, this is a correlation that shows the different features in speak, the acoustic features that I talked about above, and they show the different correlation in the what? In a different pairs. You see there is a strong negative correlation between the speech rate and the what? And the silence ratio. And yeah, so with feature engineering, we can prioritize the speech the pause durations and the different spectral energies. So from that we can get a feature that we can consider for our model to learn on and yeah, have better classifications. Yes, yeah, I think my colleague can take over. Thank you.
Yes, thank you, Gilbert. So in our pipeline, we talked about using the split architecture, and this is because of the following reasons. It was created because it's lightweight, the CNN, and has quite fewer parameters than the AlexNet, which is the predecessor. And then, so we chose this also because it has fire modules. And these fire modules are convolutions of 1 by 1 filters and 3 by 3, and these help reduce the computational cost. Then you also have the global bridge pooling layer that eliminates the need for fully connected layers. So we don't need to have very many dense layers after the bridge pooling layer. And this actually means the model is optimized for feature extraction for things like spectrograms. You also have a true SVM, quantum support vector machine, and this extends the classical SVM with quantum functions, and we're also able to map speech feature vectors into a dimensional space. We expect the stress VM to provide the better class separation and also give us an improved classification accuracy while reducing the complexity of the computation power and also maintaining a good high accuracy. Yeah, this is the function. This is the function for the USVM, and it's based on two things. First, we have a quantum kernel, which is given as the KXI, X, which takes in both the X part and the is inverse. Yeah, so we have quantum states shown here, and these are used quantum kernel function, the kx, then the bias known as b, and then the alpha I, which are known as the language multipliers optimizing decision boundaries. So this entire function is what we call the decision function. The L is the decision function, and we can improve quantum kernel function. Quantum functions can help us to improve our accuracy and separating features in the high dimensional spaces. On the next slide, why did we use the QSVM because of classical VSVM? That's because first of all, we are trying to improve the accuracy. So classical SVM struggles most times with feature spaces and deciding when you have complex boundaries. However, the HSVM enhances feature mapping by using quantum computing to improve the classification accuracy. Quantum kernel methods are able to separate nonlinear separable data. Down here, we have the quantum kernel, quantum state of creation of the input features. So the kernel formula, kernel method is the kx and the inverse x. And this simply means that what we have inside here is the quantum states, or what we call the feature embedding the data points. Yeah, so we we're able to complete the product of these two, and then try to square them, which is a similarity measure that can be used by QSVM in place of the quantum kernel. Yeah, from this combination, we expect the two outcomes. We predict that we shall have a high accuracy in the measured detection compared to traditional ML models, and also expect to have a better generalization across different languages and dialects. We say if this to be scalable AI solution can be used in resource limited settings, and also we expect it can be deployed and used in mobile applications for remote screening of for dementia. Yeah. In conclusion, we expect fish-based biomarkers to provide a scalable, non-invasive approach to dementia detection, and also expect that the combination of SquareNet and QSVM will improve our robustness and efficiency. Uh, in general, we expect AI-driven solutions to improve diagnostic cost and improve accessibility, especially when using speculated features for modeling. Yeah, so the our future work, we shall expect to do some things, but we shall expect to fine-tune the model on African languages and accents, and also improve explainability for clinical adoption, and also maybe deploy this in mobile AI-assisted dementia screening platform. Yes, thank you. That was us. Thank you, Shal.